Good afternoon, everyone. My name is Mohammed Saeed Zafar, and I am PhD student at the University of New Mexico, working with Dr. Mariam Hajati. And today I'm going to talk about designing 3D printable eco-concrete by utilizing biodegradable rheology modifiers. So this will be the outline that I will follow throughout this presentation. First, I want to talk about the bio-inspired material. So basically, bio-inspired material can be classified into 4 different families. It could be a material that could be inspired from the recycling process or how the natural material responds to different in terms of mechanical performance. And there are a lot of 3D printing attempts made by different researchers, starting from the bio-inspired architecture and toward the bio-inspired materials such as clay printing. So if we talk about 3D concrete printing, rheology and green strength, it is very critical to control both of these parameters. And Murcia et al. Suggested a tetrahedral model to discuss how different factors are interdependent on each other, and they place the green strength and rheology right at center, analogous to the oxygen atom in silica tetrahedral. So if we further talk about 3D printing requirements in terms of rheology, there are very contradictory requirements at each phase of printing. Starting from pumpability, we need a material that has a low dynamic yield stress, so that this is pumpable easily. Similarly, in extrusion phase, we need material that has sufficient dynamic yield stress and plastic viscosity, so it doesn't block the nozzle. And right after the material leaves the nozzle on the printing bed, all scenario changes. We need material now that has high static yield stress and high thixotropy, so that it can sustain the load of the layers on top of the bottom layer. So considering that importance of rheology, viscosity modifying admixtures are widely used rheology modifiers in types of material where rheology is a critical parameter, such as self-compacting concrete and also 3D printing concrete. And the viscosity modifiers are divided into 3 different classifications, starting from natural polymers. Natural polymer is further characterized into 2 classifications: natural starch and also biogums, such as xanthan-gum and also cornstarch. The second family is semi-synthetic polymers, and the main member of this family is cellulose ether, such as methylcellulose and hydroxypropyl. And finally, synthetic polymers are there, such as polyvinyl alcohol and polyethylene oxide and others. So in our work, we use all biodegradable rheology modifier, belongs to family of starch, biogums, and cellulose ether, such as xanthan-gum, methylcellulose, and 2 different types of cornstarch. This is the generalized mixed composition of different viscosity modifier. So we use viscosity modifier in different proportion as percentage weight of cement, starting from 0.5, 1, 1.5, and 2%. For the initial testing, we did flowability test and rheology testing. We used Brockfield's rheometer, equipment van shear geometry, and also we use a stereosis loop technique to interpret the different parameters such as plastic viscosity, dynamic yield stress, and static yield stress. So in the initial testing, we use all these modifiers are individual in the mix with cement, sand, and just water. So the response of cornstarch, that we use two different types of cornstarch brands. One is the capsule and other is Ultratex. So the cornstarch with capsule brand, the water demand was quite low and flowability was significantly improved with adding this. But the main rheological requirement, that is plastic viscosity and dynamic yield stress, was quite low. That it doesn't satisfy the requirement to be 3D printable. Similarly, the second cornstarch classification, in this case, water demand was quite higher and also flowability was reduced, and we experienced the same problem with plastic viscosity and dynamic yield stress, but static yield stress was improved significantly in this case. And also methylcellulose, although all the rheological requirements were in the printability range, but when we added methylcellulose content more than 1% weight of cement, the mix was very viscous that it was not easy to work with that mix, and it was not easy to print that mix. Finally, the xanthan gum. The water demand was quite higher in case of xanthan gum. The static yield stress was improved, but again, the plastic viscosity and dynamic yield stress was very low. So considering this problem, when we try these material individually in the 3D printed mix, although some of the properties were improved, but on the other hand, we have to compromise some of the parameters. So to eliminate that process, we decided to use these mixer in different combinations. But how to optimize, how do we know that this mix will be the optimized combination? So to do that manually, there will be a lot of experimental effort. So to eliminate that effort, we use a design of experiment technique, response surface methodology, and in response surface methodology, we use central composite design to eliminate that experimental effort. So as an initial input, we use design expert software, and total 47 experimentation was done to collect the preliminary data that are three responses: plastic viscosity, dynamic stress, and static yield stress. So if we talk about the interaction of three different material in the system, there was different behaviors that we can see in this. That methylcellulose has considerable effect on plastic viscosity and dynamic yield stress when we keep the cornstarch and xanthan content as the constant. But if we talk about the static yield stress, xanthan gum has significant effect on the rise of the static yield stress in the system. And we can see this here in this graph too. Okay, so after optimization through response surface methodology, the optimization suggests us around 100 different optimized mixes. We selected 4 different mixes for preliminary printability evaluation based on the value of static yield stress, plastic viscosity, and dynamic yield stress. So the first mix that contained 2% of all 3 factors A, B, and C. For the extrudability evaluation, we printed a filament with different printing speeds, starting from 15 millimeter per second to 35 millimeter per second, to get a optimized printing speed that is giving us a good extrudability. And the optimized printing speed in this case was 15 millimeter per second, and we get a good extrudability in terms of dimension consistency, conformity, and also the surface quality, as you can see, is very good. For the buildability evaluation, we printed a wall, and we measured the total height of wall, and also at 2 different intervals, like after printing 10 layers and after printing 20 layers. And this mix was buildable up to 20 different layers. And this was single layered wall with 20 millimeter dimension of the filament. Similarly, for mix 2, that has different content of both the factor A, B, and C. Again, the printing speed for this case was 15 millimeter per second, and we get a good dimension consistency and conformity in this mix too. And again, in terms of buildability and shape retention, you can see the shape retention is quite good in this case. And the buildability, this mix was collapsed after 15 years. The reason behind this is the static yield stress of this mix was comparatively low as compared to other 4 mixes, so this mix collapsed early. About mix 3, again the optimized printing speed in this case was 20 millimeter per second. And again, you can see the quality of extrudability in terms of dimension consistency. That design dimension was 30 millimeter, and we were able to achieve that exact dimension with printing speed of 20 millimeter per second. For the buildability, again, this mix was printable up to height up to 21 layers, and it collapsed after printing 21st layer. Finally, the mix 4, we try a different xanthan gum type in this case, but that leads to rise the water requirement, and you can see surface cracks in this case because of high water demand of the mix. But the mix has Good extrudability in terms of dimension consistency and conformity. The only defect in terms of extrudability was the surface quality. That was not good. You can see a lot of surface cracks in this case. Again, because of high static yield stress and thixotropy, this mix was buildable up to 23 layers. But you can see the surface quality here is also not good there. We can see a lot of cracks. And shape retention was quite good in this case too. To summarize, we get 4 different optimized mixes. Out of 4, the 3 satisfy all the printability criteria, starting on extrudability, buildability, and shape retention. And extrusion speed, the optimized extrusion speed was same for all the mixes. And also printing speed was same for all mixes except the mix 2, that the optimized printing speed was 20 millimeters per second. To conclude, we observed that the individual inclusion of these admixtures was not effective, and we saw a lot of negative impacts on the rheological parameters. And we applied the response surface methodology. That is a very effective tool to get the optimized mixes. And when we include the viscosity modifier in the binary and ternary optimized mixes, we get very optimized rheological parameters such as plastic viscosity, dynamic yield stress, and static yield stress. So the best mixes in terms of printability was mix 1 and 2. The mix 1 contained 2% of cornstarch, 2% of methylcellulose, and also 2% of xanthan-gum. Similarly, the mix containing 2% of methylcellulose and xanthan-gum displayed better printability in all the criteria. Finally, it can be concluded that all these viscosity modifier, cornstarch, xanthan-gum, and methylcellulose are quite effective, biodegradable mixes. And the ranges of the rheological parameter we found was 5 to 16 pascal second for plastic viscosity, 200 to 1100 pascal for dynamic yield stress, and 1300 to 4500 pascal for static yield stress. We are currently working on the next phases of this project, that is evaluating the grain strength optimized mixes by 2 different approaches: direct shear stress and unconfined compressive strength test. And also, it is very important to evaluate the hydration kinetics when you are using VMA in the mix. So we are doing colorimetry for that. And finally, we want to check what is the effect of adding viscosity modifier on mechanical performance in terms of compressive strength. I want to thank finally the main sponsor of this project, Transit, and other vendors to supply the material. Thank you very much for your attention.